Okay, I want to bring attention to one interesting type of problem, and it's where we'll use Stokes' theorem with singular vector fields. So singular vector fields, if you actually go through an electromagnetics textbook, you'll see these are the only ones that show up. So they're actually by far the most interesting. I think the typical example will look something like this. It will look like minus yx, and then it'll be divided by some singularity. So x squared plus y squared will be what we're considering. And this actually corresponds to the gradient of theta, where theta, of course, is just the angle in the xy plane. And so remember theta is it's a it looks kind of like arctangent of y divided by x. So if you take the gradient of that thing, you'll end up with this. So the idea is you can find the line integral where C now is any loop which contains 0. And so it turns out it does not matter. It'll be the same result, so it won't depend on C. But the funny thing is it won't be 0 because although we're tempted to use the gradient theorem doesn't actually apply unless the domain has no holes. And by the gradient theorem, I of course mean that if you take the integral of some gradient, then it's just it's basically just the fundamental theorem of calculus. You evaluate it on the endpoints, but it does not work for a closed. It does not work for a closed curve if your region has a hole. And so the origin is a hole. Right, because at the origin the function it blows up. So what you end up having to do to evaluate this is you actually have to do a line integral. But so there are two steps here. One, show that the curl of f equals 0. So if so, then the integral does not depend on C. And this allows you to choose the best possible C. So in particular, a circle. A circle is particularly well suited to this vector field, but we can only do that if we know that the curl is 0. And the second step after that is just to evaluate the integral using the simple curve and it'll be something like x equals r cosine t, y equals r sine t. And actually, why not just choose r equals 1? So then if you just do the integral with this curve, and it'll be pretty easy to crunch out. But so I think the hardest step is really we need to show that the curl of f is 0. In other words, that it's a gradient away from the origin. So let's go through that calculation real quick. really, if we know that it has a gradient representation, that we're kind of done, right? So because the curl of this will be 0 away from the origin. But let's say we had something more complicated than this, and we don't know what the gradient is. We have to take that curl. So let's take the curl of this. Okay, so we'll end up with just a couple terms. I'm going to expand the determinant along these terms here. So I'm just grouping what those determinants will look like. So first off, I'm going to use these. So minus y divided by x squared plus y squared. I'll put the jk partial y partial z here. And then finally, I'll expand the second one. And I will put the I partial x, k partial z over here. Now notice that the partial z will actually just be 0, so that's nice. So you can get away with just putting k partial x. And moreover, the f dot dr will just be used as z0. So feel free to, so we'll discard this term as well. So let's just focus on this. So we'll have j partial z minus k partial y. Yes. Yeah, okay, yeah. I made a mistake. I'm sorry. Yeah, the partial x term will not be 0. Okay, yeah. So the partial z here will be 0. Partial x will not be 0. Okay, so we're going to evaluate these. The reason the k is not 0 is because the curl, we're just trying to show the curl is 0. We're not taking the dot product with a planar tangent vector. So my apologies for the confusion. So let's factor that k out. It looks like we'll have these partial derivatives here. How many minus signs do we have? It looks like not enough. Okay, so if we do the partial derivatives, we'll just use the quotient rule as usual. So we'll get a 1. Let's see, we'll get a minus 2y squared divided by, I'm going to abbreviate this as r to the 4th. And we'll get something similar on this side. So now if we group, we'll get something like 2r squared minus 2y squared minus 2x squared divided by something. So that will be 0. Okay? So this shows that the curve does not depend on c. And I should explain why that is. So y does not depend on c. So here's the answer. I'm just going to do 2 circles just to illustrate what's going on. So it'll basically come down to Stokes Theorem on 2 different surfaces. So if we look at the surface inside that annular region, and we'll call this thing S, then the curl is 0. We know that. But now we'll use Stokes theorem. So now it'll be the integral over, let's call this thing C1 and C2. It'll be the integral of C1 minus the integral of C2. Remember that minus is there because we always have to switch the sign of the orientation on the inner one. Right, so if we use Stokes theorem, it should look like this. And so that is the same as this, but with a minus sign. So that means, so because these things are equal, that shows, if we rearrange this, that the integral of C1 is equal to the integral of C2. And so intuitively, what that's just saying is you can deform the curve as long as it doesn't hit the origin. You can do anything you want to this curve as long as it doesn't hit that 0. But that 0 is sort of like an anchor. Okay? And the idea is just that really this is also, you can also think of this as Green's theorem. Stokes theorem is probably overkill, but the idea is that the curl will be 0, and so these two things will be equal. Okay, I hope this was helpful. Thanks for watching.